All right, so now we're recording. This is class number 23 of Pkt5. It's a special class. We're going to look at a little bit of the take-home test. So if you don't have the take-home test, there's a PDF of it. I have copies of it on my front porch. And of course, there's copies in my classroom. But if you can print it off or just look at it, that would probably help. So we're going to look it all over, and we're going to maybe work. I think I'm offering the in-person students stamps to do these, do one or two a night, just to get more incentive to get it done before it's due. So we'll spend most of our time doing that. Then at the end, I want to offer up the 60 minutes. 60 Minutes, if you watch, I don't know if you're a 60 Minutes fan, but if you watch it on Sunday, they had a really good about 18-minute session on Boston Dynamics. And we've been following Boston Dynamics since they started. And they're up in Massachusetts in Boston. They just got bought out by Hyundai for like over $1 billion. But they were just a little backyard shop for a while. And then they've grown, and you see these Boston Dynamics YouTubes. So I thought it was a really interesting article, a video article on Boston Dynamics. So I'm offering that up because I know some of you need to beef up your Pkt5 notes. And so I'll give the link, and I don't think I can show that in the recording because of copyright issues. So I'll give a link, and then I'll turn the camera off, and then we'll watch it together, those that want to stick around at the end. So we'll go till about 1:35, working on take-home stuff and make this worth your while. And then at 1:35, I'll give the link to the Boston Dynamics, and then turn off the cameras. And then those that want to stick around will watch. And watching it's great, but you also ought to take some screenshots or something, or just you can write a page and get bunch of note credit for it, for the Boston Dynamics. I have students that are up there in that area doing robotics, but I don't think, there's a guy named John Rahm. He's one of my best robotics students I've ever had. He's the one that's getting his PhD from MIT. He may be doing some work for him. But they're a pretty cool company if you look to get it, if you're into computers or into robots. Okay. And for all you, we are going to start up our robotics again in the fall. So that's cool if you're interested in that. All right, so what we're going to do, though, is look at these, a couple of these. Look the whole thing over first. How about that? I'll give you some generalized hints for all these problems. So for one, and you guys can, like I say, chime in or ask a question on the chat if you want. I got that open here. But for one, let me just here, make sure your sound's high enough I can hear you. Yeah. That one, it's the only projectile motion problem on the whole sheet. It's just a bunch of stuff I made up. It's from some made up planet. Just so you can, it looks like you can tell the same height as it takes off. So it looks like it is going to be a range equation. So our generalized equation is going to be V naught squared sine 2 theta over G. It's always dangerous to use that equation, but if it says it lands at the same height that it takes off at, and it's at an angle, then it's type 2A, and its range equation will work. So there's my hint on that one. Otherwise, it's I worked it this morning. It's fairly straightforward unit analysis. No weird square roots, something like that. 2 is very straightforward. 1D, right? 1D. It's a 1D collision. It looks like it's an inelastic, so it's 1D inelastic. You have your equations there. It's one of the Kahn-Mom equations. 3, we worked one like that. That's like the last problem on, what was it? 5, 6, or something like that. It's the same kind of problem. Although, let me give you a hint on 3. Okay, so me and Dr. Fournette. Now here's the what's going to screw people up on this one. It says relative to him. So the velocity, I throw the ball at a velocity relative to me of 15 meters a second. And you have to establish here, it looks like I'm rollerblading south. What I would probably do is make south positive. You could make a negative. I don't want to work with negative numbers if I can help it. So I'm going to make south positive here. It's one dimensional, but and then it says, okay, so I'm rolling along at 6 meters a second. So if it had said that speed of the medicine ball relative to the floor was 15 meters a second, I'd plug in 15 meters a second. But it's relative to me. So I'm going, and then I throw it at 6. So 15 plus 6, it's actually 21. You got to put those two together. And that's actually 21 meters a second. Because it's called frames of reference, and the frame of reference here is the hallway and the floor, and so everything has to refer, like you can make me the frame of reference, but that complicates the issue. So you make the floor the frame of reference, so all velocities must be relative to it. All right, Dr. Fournette is rollerblading north, so obviously that's going to be negative. He'll be going negative velocity. There's his next, so that's going to be a negative 3 meters per second. Be careful there. He catches it, and then you got an inelastic collision. Okay, so this is like the problem we did with Kevin and Russ on the worksheet. And you will definitely see this one on the test. The test is also one page front and back. There'll probably be one or two of these that don't make it just because I know these take time to do, and you only have 55 minutes, so I can't put them all on there, but probably put 6 out of 8. Number 4, solve using con of mom, trig, and algebra. Do not do head to tail here. So we've got an air hockey thing moving at 7 meters a second. It strikes a stationary disk, so it meets that criteria. The masses have to be the same. One can't be moving, and they have to be an elastic collision. If that's the case, you can use that shortcut where the resulting angles, like when B is going to come off at some angle here, okay, it'll take off that way. And A is going to take off then so that these two are 90 degrees. So whatever this is, these are complementary, okay? They're not congruent, they're complementary. What's it say? It says after collision, B moves at the speed of 2.4 meters a second. So we have 2.4 meters a second at an angle of 70 degrees. Okay, so my drawing's not right, but this is 70 degrees. Therefore, I know this is 20 degrees. I know that because of shortcut. Because shortcut. Okay, so that helps us a lot. And then you're going to get, what you'll get on this one is 2 right triangles at the end. Not necessarily, I don't know how the links compare, to tell you the truth. But that one's, they're not the same. I mean, you have, okay, so, my bad. This is a terrible drawing. That is not good. Let me fix that because it really, sorry. It really messes up your drawing if you make it that. See, this is 70 degrees. So I should have read my numbers here. So that's like that. 70 degrees is like that coming down. And then this guy's 20, so he's something like that. And this, okay. So this length, as you know, make it a little longer. This length here of that right triangle that's formed has to be congruent to this leg here of that right triangle. So you can kind of get a feel for what your triangles will look like relative to each other anyway. Your 2 right triangles that are formed. Okay. So I'll highlight those. I'll do a much prettier job of this when I'm making up a key. We have a new girl. We have a new girl. She's not here. I keep inviting her to come. She's from Texas. She just joined in physics. That's got to be rough. Well, she had physics down there, but I know they're probably way ahead of us in some areas and way behind us in others. Anywho, so then I know that much. I know that's 20. I know that's 20. I know that's 70. What else do I know? I know this guy. I know the length here. Well, remember that that's 2.4 meters per second. Remember, if the mass is the same, the masses cancel on both sides, and so in this case, it is conservation of velocity. Only in this case, at an angle of 30 degrees. Here's what some students will do on the test though. They'll say, okay, I realize the masses cancel, and so conservation of velocity. They're going to say initially we have 7 meters a second. At the end, we have to have 7 meters a second. And they're going to do this. They're going to say, okay, 7 meters a second equals 2.4 meters per second plus, this is A, moving off, plus a final. This is wrong. You can't do that because there's angles involved. If it was all linear, all lined up, and it was a head-on collision, then you could just add up velocities. But because there's an angle, you have to split it up into X's and Y's and all that stuff. So you have to do summation of force, summation of momentum in the, if you want to call this the X direction, X, and then summation of force, momentum in the Y direction. Let them both equal to 0. They got to both equal each other. All right. I've confused you enough on that one. Let's go on to number 5. Number 5, now this is head to tail. So you do have numbers here, but it says complete the sketch for, oh, I'm wrong. No, I thought I was going to make this head to tail. I ended up making this components. So it is component again, only this time when they come together, it's not elastic, it's inelastic. So it sticks. And so you got to figure out, I mean, you could quickly back of the envelope, look at it and go, all right, I'm going to draw a sketch a couple of quick ghosts. If I drag it up here, I'll make my ghosts in green. This is back of the envelope, right? So I sketch out dragon. Then I know that the resultant is from very beginning to very end. That's my resultant. Now I know pretty much, I'll make my resultant in red. That's going to be the same. Now I have a pretty good feel for what my resultant should be. All right, that's going to be the combination. This is going to be P final. I can just say P final because it's A plus B, right? It's dragon plus ISS. So I already know the general where I'm going to be, but now I've got to go through, and that's your sketch. Now I got to go through and do the actual calculations. And in that case, I'm going to erase my ghosts. In that case, I've got to act, and then really, you need to have these. That may not be enough for what I just did, because you also have to come up with these right triangles. I'll make ISS blue. So I got right triangles here. In dragon, I'll make purple. So dragon comes up like this. And notice how I make these right triangles on this. Okay, they're really the right triangles, but now my components I need to make those vectors, or I'm going to get my signs wrong. Really, a component they are vectors. They have a direction and they have a length, so they are vectors. So then you put all these numbers here in there, and once again, you're coming up with what your X is going to be and what your Y is going to be. If I call this, we can start throwing numbers at it, but I'm not going to do all that. And that's, by the way, on that International Space Station, that is mega, right? That's mega, not milli. So that's megagrams. Capital M. Okay. So then you got to do the component method, which is sines and cosines, you know, legs. You got to do the legs. These two, this leg, hold on. This leg plus this leg, right? They've got to equal the resultant leg here. And then the other way, this leg is positive, this leg will be negative. And so, and that makes sense because you'll get a kind of a small value there, which you'd expect, the leftovers. All right, I think I may have drawn that to scale, so it makes it a little easier. And then finally, you have to properly describe that, give the mass, the speed, the angle, and the orientation of this guy. So this guy gets described there. All right, so number 6 is like we did, it's a lot like the one, well, it's an elastic collision. So it is kind of like the one we did in class on 5.8, 5.8.6. This is a lot like, if you want to look at some template there, this is like 5.8.6, okay? Use that one. And you know what? Somebody asked this question. They said, are help videos of these available through, through the YouTube channel? Yes. This is not a practice. Some of these have. I think this one may. Some of these have help videos, but watch out, I may change numbers a little bit. But I'm not giving you QR codes. I mean, this is actually a test. You're supposed to try it on your own, not just watch a video. But if you need help, you might find a video. And those videos on that channel are in playlists. If you look at if you sort by playlist, it'll have like 2D collisions, conservation of momentum, all that kind of stuff. Now the last couple here is 7 and 8. Now 7, we just got the table filled out. This is not the same table as on sheet 5.9. But it's the same kind of thing. You're doing duck walk lab. You're increasing the force, and this time instead of the delta x being 3 meters, the delta x here is 4 meters. Initial velocity is still 0, but then I gave it times, and then you got to figure out acceleration. Well, remember to find acceleration, we have delta x, we have v naught, we have t. You tell me now. Okay, see here. You tell me, what equation would you use to find acceleration? This session is like a pre-help session. Monday night we'll do another session from 9 to 10 on this test, and then I'll make available the video, a nice version of this video key where it's all worked out, and I'm explaining each problem. That'll be available Wednesday next week, Wednesday afternoon. Anywho, so question real quick. How would I find this acceleration if I'm given delta x, v naught, and t?
We use the second orange.
That's it. There's the couple of points there. Second orange, what I'm looking for. So I'll just go ahead. So we know our equation we're looking for here is delta x is 1/2 at squared. We're trying to solve for a. So a is 2 delta x over t squared. And so that's going to give you the A column there. Once you have that A column, you're going to plot, then you're going to plot this column. That's why these are highlighted. This column versus this column. This column will go on this axis. This column will go on this axis. The dots. Then you're going to connect your dot, or not connect your dots. You're going to get a best fit line. And that will, I'll leave it up to you, but that will be enough to understand the mass of the cart. But that's something we'll also do tomorrow in class. So if you want to hold off on 7 until tomorrow, 8 we're going to do in class. I don't want to give too much away on that. We'll do that that will be probably Friday. Yeah, that'll be Friday in class. We'll work on one like number 8, okay, or Friday at our video, Friday afternoon. Okay, so there's the whole test. Now, if you want to get credit, if you're an in-person student, you'll get a stamp if you'll do number 1. Tonight. and have it ready for tomorrow. Sorry, I can't offer any little things like that for virtual that I can think of. All right, now I want to show you. Let me stop that sharing. And I want to share with you what I'm talking about on this Boston Dynamics. Here it is. Here it is. Here it is. Here it is. And then I'll let you go. Hold on. Come on, man. Where'd you go? Okay. I had it on the weather. Okay, here it is. Okay, so here's what I'm talking about. It's the if you'll just type in 60 minutes Boston Dynamics, it'll pop up, and I'll put the link in the comments for this, and you don't have to watch it today. I thought if I'm going to stop recording and I'll watch it with you if you want to stick around. But it's pretty cool. Maybe we'll pause it and talk about a couple aspects of it. It's about 13 minutes long, it looks like. So I'll put the links in the comments, and otherwise, I think we're good. So you guys can take off. If you want to stick around and watch this with me, that's cool. If not, I'll watch it by myself. All right, so you. And we're going to, I got to stop recording.